All right, listen up, everyone. You're here because you are dead serious about crushing the BSNL 2026 Senior Executive Trainee Exam, right? Well, consider this explainer your elite, zero-fluff cramp session. We are bypassing all the basic background noise and going straight for the jugular, the high-yield formulas, the core mechanisms, and, honestly, most importantly, the exact traps those test makers are going to use to try and steal your points. So get your notebooks ready, get focused, and let's dive into this high-intensity review. We're going to maximize that technical score today.
Okay, here's our relentless game plan. We'll run through signal processing fundamentals, continuous wave modulation, pulse modulation, and PCM, DPCM, and delta modulation, multiplexing techniques, and finally, spectrum management. Let's move. Starting right off with Section 1, Signal Processing Fundamentals. Let's talk Nyquist limits and antenna requirements.
First things first, we got to lock down the absolute fundamental limits. For the Nyquist theorem, to completely recover a message signal without getting that nasty aliasing, your sampling rate, fs, has to be greater than or equal to 2 FM, where FM is your maximum message frequency. Now pay attention, because here is the major trip-up zone. Do not, under any circumstances, confuse the Nyquist rate, which is 2 FM, with the Nyquist interval, which is the inverse, 1 over 2 FM. They love testing that distinction. Also remember your minimum antenna height, h, equals lambda over 4. Lambda, of course, is the speed of light divided by frequency. Test makers are notorious for giving you a frequency in kilohertz or megahertz here. If you forget to convert that back to pure hertz before plugging it into the equation, your antenna height calculation is going to be wildly wrong. Secure those easy points, guys.
Moving fast to Section 2, Continuous Wave Modulation. We're putting amplitude and frequency modulation head-to-head.
Okay, for amplitude modulation, you need these formulas memorized cold, no excuses. Modulation index mu is just your message amplitude over your carrier amplitude. Total power is carrier power multiplied by 1 plus mu squared over 2. And bandwidth is simply 2 FM. But let's talk about efficiency, because this is highly testable. So much power is totally wasted just transmitting the carrier wave itself. So maximum efficiency only happens when your modulation index mu equals 1. If you plug 1 into that efficiency formula, you get 1/3. The classic exam trap is trying to trick you into assuming 100% efficiency is somehow possible in standard AM. It is absolutely not. Max efficiency is exactly 33.3%. Keep that number in your back pocket.
Now flip over to frequency modulation, or FM. Here, our modulation index is called beta, and it's equal to the frequency deviation, delta F, divided by FM. The critical trap here is calculating the bandwidth. Please don't mix this up with AM. FM bandwidth is governed by Carson's rule, which states the bandwidth is 2 times the total quantity of FM plus delta F. You literally have to remember to add that frequency deviation in there. You can also write it out as 2 FM times the quantity 1 plus beta. Just don't forget Carson's rule.
All right, Section 3, Pulse Modulation and PCM. This is where we look at the analog to digital conversion pipeline. Before we hit true digital, let's get the matrix of analog pulse modulation completely straight. PAM, PWM, and PPM. It's literally all on the names, guys. Pulse amplitude, pulse width, and pulse position. For each specific type, only one characteristic varies, while the other 2 stay perfectly constant. Now, here's the guaranteed exam trap, the bandwidth hierarchy. Because PAM varies the amplitude, you might logically think it's the most demanding on the system. Actually, scratch that, it's the exact opposite. It's the lowest. PPM, pulse position modulation, requires the absolute highest bandwidth of all 3. Lock this into your brain right now. PAM is low, PWM is medium, and PPM is high.
Okay, now we are officially crossing over into true digital territory, pulse code modulation, or PCM. This is a massive area for exam calculations, so stay with me. Your quantization levels, L, equal 2 to the power of n, where n is your bits per sample. The step size, delta, is your peak-to-peak voltage divided by L. And your maximum quantization error, that's always going to be plus or minus delta over 2. Here is the conceptual trap they love to spring on you, thinking the whole PCM pipeline is reversible. It's not. Encoding is reversible, sure. You can decode binary back into discrete voltage levels, but quantization, that introduces a permanent error. The second you round a continuous analog wave to a discrete step, that original exact value is gone forever. Just remember, quantization is irreversible.
I'm actually going to pause right here for emphasis, because this formula, it's basically free points on exam day. This is the formula for signal to quantitation noise ratio, SQNR, expressed in decibels. 1.8 plus 6n. What this brilliantly shows is that for every single bit you add to your sample, meaning every time you increase n by exactly 1, your signal-to-noise ratio improves by exactly 6 dB. It's a beautiful, constant rule. Committed to memory for sure.
Let's keep this momentum going. Section 4, DPCM and delta modulation. It's all about achieving bitrate reduction.
So let's directly contrast standard PCM with differential PCM, or DPCM. Standard PCM encodes the absolute raw sample value, right? If the voltage is 4.7, it explicitly encodes 4.7. DPCM is smarter. It uses a prediction filter to literally guess the next value. Then it only encodes the difference, the prediction error, between the actual sample and its guess. Because this error is almost always a really tiny number, the dynamic range shrinks dramatically. A smaller range means you need fewer bits, which directly lowers your bitrate and your bandwidth. The absolute critical takeaway here, DPCM quantizes the prediction error, never the original signal.
If DPCM is efficient, delta modulation, or DM, takes it to the absolute extreme. It uses a 1-bit quantizer, meaning n equals exactly 1. You're only sending a 1 to step up or a 0 to step down. That's it. Because n equals 1, we run into a major exam trip-up zone. The standard bitrate formula is RB equals n times Fs, right? But in delta modulations, since n is 1, the bitrate is exactly equal to the sampling rate. RB equals Fs. Do not let them trick you if they ask for the bitrate of a DM system and only give you the sampling frequency. It's a 1-to-1 ratio.
Of course, getting that amazing 1-bit efficiency comes with a serious cost. Tracking errors. This is a guaranteed exam question setup, I promise you. You have to perfectly match your step size to the signal. Think of a leaping kangaroo. If your signal is changing really rapidly and your step size is too small, you get slope overload. The staircase simply can't keep up with the jump. Conversely, picture a really slow turtle. If your signal is totally flat and your step size is way too large, the system just oscillates wildly up and down around that flat line. We call that granular noise. Do not reverse these two. Overload means the signal is too fast and outpaces the step. Granular means the step outpaces a flat signal.
All right, Section 5, multiplexing techniques. We're talking FDM, TDM, and CDM. Let's look at time division multiplexing, or TDM. This assigns digital signals to distinct time slots. The base bitrate formula is pretty straightforward. Bits per sample, n, times number of channels, n, times the sampling frequency, Fs. But here is a particularly vicious exam trap. To keep the transmitter and receiver perfectly aligned, systems add synchronization bits, usually denoted as A, to the end of every frame, so the formula becomes the quantity n times n plus A, all multiplied by Fs. Listen to me carefully here. You absolutely must add those sync bits to your channel bit count inside the parentheses before you multiply by the sampling rate. If you multiply first and add later, you will get the wrong answer every single time. Let's do a rapid-fire summary of the big three multiplexing approaches: FDM, TDM, and CDM. FDM separates users by frequency and requires guard bands. TDM separates by time and requires synchronization. But take a good look at CDM, code, division, multiplexing. The trap here is assuming CDM carves up time or frequency like the others. It doesn't. In CDM, all users transmit at the exact same time on the exact same frequency. How? They are separated purely by unique orthogonal mathematical codes. This is spread spectrum technology in a nutshell, and it gives massive security and noise immunity advantages. Home stretch, everyone. Section 6. Spectrum Management. Global allocations and regulatory bodies. The radio spectrum is basically a limited natural resource, extending from 3 kHz all the way up to 300 GHz. You just have to memorize these 4 bands exactly, no way around it. AM radio is 300 kHz to 3 MHz. FM and TV sit in the 30 MHz to 300 MHz band. Mobile communications operate from 300 MHz to 3 GHz, and satellite takes over from 3 GHz up to 30 GHz. The classic trip-up? Mixing up the starting point for mobile and satellite. Just use this trick. Mobile is mega, starting at 300 MHz. Satellite is giga, starting at 3 GHz. Lock that in.
Finally, who actually governs all these frequencies? Globally, it is the ITU, the International Telecommunication Union. But if the exam asks for the regulatory body specifically in India, please do not fall for the distractors. Test makers will throw TRAE, BSNL, or ISRI at you to see if you bite.
The correct answer for spectrum management in India is the WPC, the Wireless Planning and Coordination Wing, which sits right under the Department of Telecommunications. Memorize that acronym, WPC.
All right, let's finish this explainer with a rapid-fire mental test of your reflexes. A PCM system has a bitrate of 64 kilobits per second and a sampling frequency of 8 kilohertz. How many bits per sample are used? Just recall your core formula. Bitrate equals n times fs, so 64 equals n times 8. The answer is exactly 8 bits per sample. If you nailed that instantly, you are absolutely primed, tested, and aggressively ready to crush the BSNL SET exam. But before you go, I want to leave you with a thought. As global telecommunications increasingly abandons these legacy analog limits from massive 5G arrays and crazy optical networks, how will these exact same fundamental mathematical rules continue to govern the wireless tech of tomorrow? Keep that in mind as you do your final reviews. You've got this. Good luck.